Okay. Am I audible?
Yes, sir, you're audible.
Okay, thank you. So it seems that nobody have joined till now. So maybe they will join in some time. But still, I think it will be fine if we start. So okay. So welcome again. So welcome back to the problem solving session of the NPTEL course Fluid Mechanics and its applications. So we are in the week 4 of this course, and unfortunately, because of time constraints, we were not able to deal with the Reynolds or the fundamentals or at least the definition of the Reynolds transport theorem in the previous session. So I just thought that it would be good to go through it, and moreover, since today's session mainly deals with the application of Reynolds transport theorem and obviously simplified form that turns out or the it one or eventually when we apply this theorem itself to the energy conservation and simplifying the energy conservation equation for certain assumptions, we finally obtain the Bernoulli's equation. So since it has a far-fetched implication in the field of fluid mechanics, so I felt that it would be good to start with it. So in simple terms or in simple words, the Reynolds transport theorem acts as a transformation from the control system to the control volume approach. Okay, so I guess I should write it. Control system to the control volume approach, RTT acts as a mathematical transformation to the governing equations, obviously. And why do we need to do so? It's because of the very fact that all the conservation equations, right? Because as I usually tell to anyone who is new to the field of fluid mechanics, that all the problems or what to say concepts of fluid mechanics would boil down to these three fundamental laws. Like any concept or any problem can be approached by following or understanding these three conservation laws. That is mass conservation, momentum conservation, and by momentum I mean both the linear and angular momentum, and the energy conservation. Okay, so any problem or concept in the domain of fluid mechanics can be approached by going through or starting with or initializing any problem with by checking that whether these three conservation laws are satisfied or not. So implying that or implying these conservation theorems, we can approach any fluid mechanics problem. So that's one of the most important point that I wanted to say. But the issue was that when these laws were initially devised, right, when these laws were initially formed, they were formed for a control system. Like they will define for a system with a particular definite mass. Okay, that's the control system approach. So these were defined for the control system approach. But and that basically in the language of fluid mechanics, that basically tells us the Lagrangian approach. The Lagrangian approach. So all these laws were well defined or well formulated for the control system approach, right? Because initially it was formed like for this kind of approach only, the control system approach. Okay, but since we discussed in the previous session that how the control volume approach acts as a very good alternative, I would not say substitute, but a good alternative to solve fluid flow problems by simplifying the tedious nature of the our problem. Like if we go on to solve the fluid mechanics problem by following the Lagrangian approach, by following each and every fluid particle in the flow domain, then it will get give us very accurate results, but it will be very tedious and it will be very difficult job to handle all those governing equations for each and every fluid particle. So that will be a difficult and tedious job. But and to avoid that, or in order to skip past such tedious nature, we saw that how the control volume approach helps us to eliminate such tedious calculations, right? And how it came out to be very useful for most of the fluid flow problems that we are going to deal with in this course. But since the laws were only defined for the control system approach, mathematicians developed the Reynolds transport theorem so that the initial governing equations that were devised for control system could be transformed from a control system to a control volume approach. Okay, and thus in this way RTT, the usefulness of RTT comes into picture. So the derivation of RTT I guess I won't do right now because it is being thoroughly discussed in the video lectures, and I suggest that you follow to the video lectures or any standard fluid mechanics book, or itself the book by Professor Gupta that is titled Fluid Mechanics and Application. So you may refer that book, and there a very clear derivation of the RTT is given, and so you will get a very good idea what it actually means or what mathematically you are trying to achieve. But just to give an overview, if n is a fluid flow parameter, okay, it can be velocity, pressure, mass, anything. Okay, if n denotes a flow parameter, then the rate of change of that flow parameter in a control system approach, okay, in a control system approach would be equal to the local change of that parameter at a, in the flow domain, the local change of that parameter in a flow domain plus the net outflux of that flow parameter through the control volume or the control volume that we have chosen. Okay, so this is actually the very definition that I wanted to give, but just to tell you each and every term, here capital N, I will write it here, capital N denotes a flow parameter, so I will write this a flow parameter. Okay, and T obviously d by dt denotes the complete derivative of that flow parameter in a control system approach. So d by dt denotes the complete time derivative, okay, the complete derivative of that parameter in a control system approach. That's important. And dou by dou t denotes the local change of that flow parameter with respect to time. So that's why only partial derivative is used. And here eta or small n, not eta, okay, small n denotes the intensive the intensive flow parameter that we are going to choose, right? If n denotes the flow parameter, the small n denotes the intensive flow parameter of that same parameter. Okay, so intensive flow parameter. So since only Sriniket is there, so Sriniket, can you please tell me what an intensive property or flow parameter usually means? Am I audible, Sriniket? Yes. So could you tell me what a intensive flow parameter?
Hello.
Yes, yes.
Hello, sir.
Yes, yes.
Sir, intensive is like which is individual, means it does not depend on the other factors such as area.
Okay.
Basically, we can say it as it does not depend on other parameters.
Okay, area what you have told is actually correct, but I would say that if you're going to treat it more specifically, intensive property, I must say, in a exact definition would be a flow parameter that does not depend on the extent of the system, of how large or how extensive our system is. It does not depend on the extent of the system, and in specifically for this case here, a intensive parameter basically implies the value of the parameter per unit mass. So small n would basically give us capital N divided by mass. Okay, the mass of the flow parameter. Okay, in this case.
Sir, is it like it is only at a particular point?
Not necessarily, because if you are dealing with a control volume, then it will certainly have a definite area or volume, right? It will obviously have some definite footprint. It will have some particular area that it covers, right? So it does not mean for a particular point. Okay, is that fine?
Yes, sir.
Okay.
Yes, sir.
Okay, so that's the case. And so n, we have looked into it, capital N, small n, and V cut, like this one, basically denotes the volume of the control volume. Okay, the control volume that we have chosen, this CV. So dV basically denotes the integration of, it is the elemental volume of that control volume. So integration over this integration basically denotes the integral of the flow parameter throughout that control volume. Okay, so this is that. Then the second term, this term basically denotes the net flux of that flow property across the control volume. Basically the net outflow minus the net inflow of that flow parameter in that control volume. Okay, so here again rho denotes the density, n is the intensive flow parameter. VR, okay, it's important here. VR in general, it is a generalized form, so it will have VR. So VR is the relative velocity of the fluid or flow with respect to the control volume. Okay, it's not the absolute velocity, but the relative velocity of the fluid with respect to the control volume. Okay, so it is relative velocity. It's very important. Like sometimes this is missed out, but I would like to emphasize that it is the relative velocity.
Sir, is it relative velocity with respect to the flow?
Yes, the flow would have its own velocity, right? It will come or leave the control volume with its own velocity. But guess that if the our control volume itself is moving, then it will definitely have a relative velocity. The fluid will definitely enter or leave the control volume with a relative velocity respect to its velocity of the control volume, right? So it is a relative velocity and not the absolute velocity. Is that fine?
Sir, I just have one doubt. Like you have said that relative velocity of fluid with respect to control volume.
Yes.
Since the control volume is like a tube, we can assume it is some tube.
Okay.
So when the fluid is flowing through the tube, is it like the velocity of a particular point?
No. Velocity of that fluid. Just assume that the velocity with which the fluid with which the fluid enters your tube. If you have considered a tube as a control volume, then just assume the velocity of that of the fluid at that inlet. Okay. Now since you are asking mentioning of particles, see as a in a I guess in the second week or in the first week itself, we have discussed about the continuum nature, right? So we don't deal with discrete points, right? We don't deal with discrete velocity value of the velocity at discrete points in the flow domain. Rather, we believe that the flow, the velocity would have a continuous behavior or a continuous nature. The change, even if the velocity changes from point to point in the flow domain, it will behave in a continuous manner, as a smooth function, right? A parabolic nature or a cube or a say different curve, but it will have a continuous nature. It will vary continuously. Okay, so let me draw it. So it will vary continuously. Say it's a parabolic profile. Since you are mentioning a tube, and I assume if it is a circular tube, so it will have a parabolic velocity profile. Okay, and now see here in this case the velocity is changing from point to point. Okay, at this point the velocity is different. It is essentially zero in this case. Then its velocity increases. Then up till the center line the velocity has its maximum value. Then again it decreases because of viscous effects. So here till now we have not touched upon the effects of viscosity, or rather I would say the effect of boundary layer, how boundary layer is formed, and what are the implications of viscosity in a flow field, right? Since we are not dealing with that, so we are just assuming that it has a uniform velocity, right? Since viscous effects are not considered, so at the inlet it will have a uniform velocity. Okay, say 3 meter per second. Then this is the value that we have to consider at the inlet. Then again at the outlet. But if your tube that you have chosen itself is moving, then the fluid would have a relative velocity with respect to fluid, right? Do you get that? See, if the fluid is entering, is approaching the tube with 3 meter per second, say, okay,
yes,
and your tube itself is moving in the same direction, say with 1 meter per second velocity, then what is the relative velocity of fluid with respect to the control volume?
It's 2 meters per second.
Yes, right. Since they are moving in the same direction, thus the relative velocity of the fluid with respect to the control volume is now 2 meter per second, not 3 meter, not 3 meter per second. Okay, so this is the gist, that we have to consider the relative velocity and not the absolute velocity. But in some simplified scenarios, say if the velocity, in most of the cases we see that in our day-to-day applications, we may encounter a scenario where our control volume is fixed, is stationary. So in that case, this VR will become equal to the velocity of the fluid. Okay, so this is the simplification. But in general case, this is the relative velocity of the fluid, not the absolute velocity. Okay.
Yes, I got it.
Okay. So actually this definition should have been dealt in the week 3 session, but since we had time constraints, so we had to skip past it. So okay, so in this week's session, we will basically deal with the integral forms of the conservation of mass equation. This is basically mass conservation. Then again we'll see how to use the differential from the mass conservation, or basically how to derive the differential from the mass conservation from the integral form, and the use of stream functions. It's a very important topic, so we'll look into it. Okay, so again I won't go to all the definitions here, I'll just go to the gist of it. So if from the mass conservation applying RTT, we obtain that dm by dt is equal to rho AV in minus rho AV out. See, this is very simple actually. This can be directly achieved by applying RTT. So say
Hello, sir.
yes.
Sir, I just have one question out of the topic, sir.
Okay.
Sir, don't we deal with energy losses?
Yes, that's the thing, right? Energy losses, when does it come into picture? When we are regarding the viscous effects, right? The effect of viscosity,
Yes,
we are encountering with
but,
tell.
yeah, but in energy losses also we'll encounter with Reynolds number.
Reynolds number. See, Reynolds number would exist even if we don't consider the viscous. Reynolds number will only consider when we have viscous effects, right? That's for sure. But here at least in this point, at this point of the course, we are not considering the viscous effects. See, when we usually eventually go through this today's session, we will see that most of the problems that we are going to discuss, we take an assumption that the flow is in viscid. So if the flow is in viscid, then we tell that the viscous effects are not considered. So since the viscous effects are not considered, the effect of viscosity will not be felt by the fluid. Okay, and since the fluid won't encounter the effect of viscosity, the effect of walls, I mean, like, since the container or the confinement through which the fluid passes, say if it's a internal flow, if the flow itself does not feel the effect of those walls, then how can you say that the velocity profile would be modified because of the effects of the wall, right? Since the cause because of which the effects of wall is felt itself is not there, that's why the velocity profile remains uniform. You will see that how we are assuming that, and that in turn that simplifies all our problems. So that's the case, but it's a good thing that you have asked. Though the energy losses usually comes in, at least in fluid flow, it comes to because of the effects of viscosity. Okay, and it can come to other cases also, but we basically deal with viscous effects only, viscous losses only. So that's the thing.
Okay.
Okay.
Thank you.
Okay. So this equation, as I was mentioning, could directly be achieved through the application of RTT in mass conservation. So if we take our capital N as M, that is mass, right? Then small n will basically give us M by M, so it will basically give us 1. So applying RTT in this case, so dm by dt for the system would be equal to dou by dou t for a control volume. Then since n is equal to m and small n is equal to 1, then it will basically be rho 1, then dv plus integration in the control surface rho Vr, then since there is no n, then it's basically 1, then dA. So it will basically give us let's just cross check if you are correct or not. So we need to consider the normal vector. I'm sorry, that's why I was first verifying. So here it will be 1 actually. So and then Vr dot eta cap normal vector. So otherwise, if you are not considering normal vector, the this area integral would have a vector sign. So we need to deal with that. So it will be rho Vr dot n cap dr. Okay. So the first term is same, these two terms, this term and this term is exactly the same. This will go to 0 because since we know mass in this case, since there is no addition of mass to the system, so the net change in mass, okay, so let me add the student. Okay, so the net change in the mass in the system would be 0. So the first term you can correlate that this term and this term is identical, and as I told, this term will basically give us a net outflux, right, net efflux, or as they say, from the control volume. So if the density is constant and the velocity profile is uniform, then you will see that this term eventually simplifies to these terms. Okay, so I won't go to the simplification. It's quite obvious, since the rho is constant, V is uniform, then integral of the area will basically give us A, right? So it will basically give us rho AV in minus rho AV out at our inlet and outlet. So this term simplifies to this. Okay, so this is basically a statement. The rate of change of total mass contained within the control volume must equal the net influx of the mass. Okay, so I guess it's simple. I won't go through it again. So for steady flows, we again consider this equation, dm by dt is equal to rho av in minus rho av out. So Shriniket, are you still there?
Yeah, yes, sir.
Okay. So can you see how the effect of, since the effect of viscosity was disregarded, how we obtained this term from this equation? Can you tell me? You can try. There's no pressure in it. Like, it's fine. We just
Yeah, yes, sir. Here, the density of the fluid will be equal throughout the pipe.
okay, assuming that it's
And
incompressible.
the
Yes.
incompressible fluid and the area is also equal. And here we will be having PR, which is the relative velocity of the fluid with respect to the normal vector.
Okay.
Yeah, so when we do I think about dot product or
Dot product.
yeah, yes, sir, that is the relative velocity in dot product of normal velocity when we do those, and I think we'll be getting the volume.
Okay, that's fine. Thank you, Sriniket. I guess there's one more student here. So, it's Francis. So, I hope I am pronouncing it correctly. So, Francis, am I audible?
Yes, sir.
So, have you attended week 4 lectures of this course?
So I haven't seen it or.
Oh, that's fine. That's fine. No issues. You can just, if you want, you can just follow this session. Then just, since I will not be dealing with all the concepts here thoroughly, I would suggest that you look into the week 4 lectures. That if you are planning to join the course and get the proper certification.
Actually, will we be doing any numerical problems here?
Yes, I will be dealing in the, since it is a it is agenda that I look into the concepts at first and then thoroughly then eventually go look into some numerical problems. So I'm going to follow that regular agenda. But like, if you want, then you can stay. Otherwise, you can join after a few time also. That's after some time also. That's no issue. But since there is an agenda that I have to follow, I have to go through all the details first and then go to the problems. Is that fine?
Yes, sir.
Okay. So thank you, both Francis and Sriniket. So here basically what I meant to say, that since Sriniket was mentioning about the effect of losses in the flow field. So since and as I told, this comes into picture when we regard viscous effects. So the implication of disregarding the viscosity comes here in this integral. Since VR, since if the viscous effects are considered, VR would not have been uniform throughout our cross section or throughout the cross section of our inlet or outlet. Okay, then we had to say, even if the density is constant, then we eventually we had to evaluate this integral separately and then find out the value of this integral. Obviously it would have some limit, this integral will have some limit. So after evaluating that only, we can find out the local rate of change of mass. Okay, but since in this case I told that the velocity remains uniform because we are disregarding viscosity.
So,
Yes.
so in this transport equation, can you explain why we are using a controlled surface term? I mean, actually, the fluid will be entering into the controlled volume usage. So, why we are actually concerning about the controlled surface?
Okay, that's fine. Thank you. Why? Okay. So yeah. See, it is not that what I am considering or what is considered here. It's actually the general structure of the governing equation that has been formulated. Okay, see, the control surface, it is a control surface and not to be confused with control system. Okay, it's control surface. So any control volume would inherently have a control surface adhering to its boundaries, right? So it is the control surface. So rather than having evaluating a volume integral, we will be dealing with area integral in this case. Okay, that's why we are dealing with control surface. But even if you are saying that or questioning the validity of the control volume approach, this integral can be transformed into control volume approach by applying the Gauss divergence theorem. Given that the control surface, covers or engulfs the entire control volume. If that's the case, then we can apply our Gauss divergence theorem here in this case, and then transform this equation into a this integral into control volume or a volume integral, and then this right hand side of this equation, the RTT, would transform into the evaluation of volume integrals rather than regarding control volume and control surface separately. So that can be done, but there is no issue in having control surface while considering the control volume or the Eulerian approach. Okay, this control surface should not be confused with the control system. Okay, so I guess I was clear.
Okay, sir.
Okay, thank you. So thank you. So okay, say I guess this effect also I was able to clarify, like why this regarding viscosity helps in simplifying the term to rho AV. So
Yeah, yes, sir.
okay, thank you. If it is constant, the volume velocity will just come out. It will come out, and it will basically be the integral of the area, right? So it will give us whatever the area may be, A1, A2. So if it's 2 to 1, say, then it will basically give us rho 1 A1 V1, sorry, rho 2 A2 V2 minus rho 1 A1 V1. So that's the simplification. Okay. So for steady flows, what they are telling that since the flow is steady, so the derivative respect to time, or the local derivative, or I must say or the local derivative respect to time would be 0. So if this term goes to 0, we can say that rho AV in is equal to rho AV out. Then again, for constant density, which is a very good assumption when we are dealing with high density, highly incompressible fluids, for example water. Like since water is a fluid that has a very vast implication or uses throughout our throughout the engineering field. So that's a very good assumption. So considering that, if density is considered to be constant, this equation simplifies to AV in minus is equal to AV out. So basically, if the inlet is denoted by 1 and outlet is denoted by 2, then we can simply write it as A1 V1 is equal to A2 V2. So it is a very though it is a very simplified form of the mass conservation, but I would say it's a very elegant equation that gives us a very good idea, or at least a very good understanding of how the flow behaves because of area variation. Okay, again, see, let me give an example. Okay, say we are dealing with a nozzle. Okay, so nozzle basically means that the outlet would have an area lower than the inlet. Okay, smaller area than the inlet. Say this is 1, sorry, so this is 1, the inlet is denoted by 1 and outlet is denoted by 2, and this is the direction of flow, say. So considering the continuity equation given by this, for obviously for steady flow constant density, can anyone of you please tell me how would the velocity behave? Like, what is the relationship between V1 and V2? Like, which would be greater, smaller? Could you tell?
V1 would be smaller and V2 would be greater.
Yes, thank you. It's a very simple understanding or simple observation, which we see that if this equation is valid, and we are seeing that okay, seeing that a1 is greater than a2, so it will be to satisfy this equation we must have v1 lesser than v2, and this is exactly what being seen in the case of nozzle. Even if we are considering the viscous effects would be there, because it's a practical case, right? A flow through a nozzle is a practical case, is well defined practical case, so viscous effects are already there, inherently there. But since even after that, a simplified version of the mass conservation, a very simplified assumption where we have disregarded the viscous effects, thus this constant uniform velocity profiles, and we have disregarded the change in density from cross section to cross section, and assuming a very incompressible flow. So given that scenario also, we are getting at least an idea that if the area at the outlet is lesser than the area at the inlet, and given at least a steady flow, we would have a higher velocity at the outlet, right? And this is exactly what we see in our day-to-day cases, day-to-day life scenarios, right? A very simple example is that how we used to increase the velocity of the flow through the outlet of a pipe by pressing its exit, right? We try to pinch the say this is our fingers, so we try to pinch the outlet of this pipe or hose, I would say pipe, so that the effective area of the outlet is compressed. So even if the velocity at the inlet was having certain value, when the outlet area is decreased, we see that the liquid pours out or moves with a higher velocity, right? So this is a very simple observation that we usually see. So that I wanted to mention. Okay. Okay. Who is speaking? Both Prabhajan and Francis have their mic on. So is it Prabhajan?
No, sir.
Oh, Francis. Okay, so that's fine. Okay, Francis, please ask.
So actually, when the area is reducing, the velocity is increasing and pressure will be reducing, isn't it?
Pressure.
Pressure term. I mean, when the area is reduced, in that point, the pressure term will be reduced. I am having some confusion with actually the pressure is actually forced the area is. So when the area is reduced, so the pressure should be increased, but the pressure term is actually reducing. So can you explain that?
Okay. Thank you for the question. But first of all, we must understand that this relation of, I guess you are basically implying, if we are dealing with in the domain of fluid mechanics, you are basically implying this relation, I guess. The Pascal's law. Say if you are regarding the Pascal's law, Q1 equal to P2. Say, I got your question, but I'm just trying to approach with the fluid mechanics point of view. Then we say that F1 by A1 is equal to F2 by A2. Okay, and you are saying that if A2 is going down, then you are saying that P2 should go up, right? Since pressure is equal to force per unit area. If area is going down, pressure should go up. See, this relationship, I must say, has a very proper implication. Like if you are planning, if you are trying to apply it, has an implication in the case of what to say, static fluids. Okay, fluid statics, in the domain of fluid statics, that if the flow is stationary, then this relationship seems to be valid, obviously applying some certain assumptions. Okay, that's first thing. But since now we are dealing with fluid dynamics, right? The flow is in motion. So this area relationship with pressure forces, this fails to be valid. Okay, this fails to remain valid since we are dealing with now uh, fluid dynamics, right? The flow is now moving, it is having some certain velocity, and the velocity or the motion of fluid itself will have certain effect on the variation of pressure in the flow field. Okay, so we cannot directly imply that area reduction would imply increase in the pressure. Okay, and eventually we in fact see that even if the area is reduced here, uh, the pressure will also reduce in this case. Funnily enough, contradicting to what the usual notion that we have, even if for a subsonic flow, like lower Reynolds number flows, for subsonic flow.
It only works on the fluid statics, and for the fluid dynamics,
Yeah.
it's actually it will be different. I mean, the noise equation will be used.
Yes, it will be different since the
Okay,
fluid motion will have some implication on the variation of pressure, right? So we cannot directly relate it, and moreover, I guess this definition of pressure is equal to force per unit area is a very what I must say, very fundamental definition that only comes into picture when we are when the pressure is known. When a pressure is known, area or the force is known, and the area is known, then we are going to find out the pressure. But here in this case, do we have any proper definition of force here? Like, we are not defining force itself. Fundamentally, this definition will not at all be applicable in fluid dynamics. But I'm just saying that the definition of force, area is force or pressure is not completely well defined in this case, right? We are, or in simple sense, we are not dealing with it right now. It's just simple mass conservation. Okay, the implication of pressure actually turns out when you are dealing with the conservation of momentum. Okay, in that case you will see how the pressure actually behaves in the case of fluid dynamics. So we will look into that when we are dealing with momentum conservation. Is that fine?
Okay, so one more thing is we only can use that force when there is a viscous term. I mean, simply here actually we are having an assumption in this non-viscous fluid.
See, yes, you are correct, but force does not necessarily be because of viscous effects. Force can be because of the pressure gradient also, as well as the body forces, right? The forces, for example, gravity, electromagnetic forces. These kind of forces can also have, can be regarded as forces that drives the flow. Okay, so we cannot only say that viscous effects would have the effect of which only act as force in the case of fluid dynamics. So I guess that's the case. Okay then. So now we will be dealing with some simple cases, I must say. So here we are dealing with flow through a circular pipe that is laminar, basically laminar flow through a circular pipe. Okay, here I must say the domain is defined, the geometry is defined. I must say it is a circular pipe. So this would be our geometry, and say this is the direction of the flow, and we are being told that the flow follows a parabolic velocity profile. So more correctly. Okay, and whose governing equation, say, and if this denotes Vmax, the maximum velocity that inherently is being understood to reach at the inlet, at the middle or the central cross section of the pipe, because this is the point which is farthest away from the wall. Okay, so here we are seeing that how the viscous effects have modified the velocity profile. Is that now obvious, Sriniket, how the velocity profile changes because of the effect of viscosity?
Yeah, yes, sir.
Okay, See, actually this result that we are getting, it is actually an exact solution of the Navier-Stokes equation. Again, Navier-Stokes equation. I briefly discussed it in the previous session, but again. So it is the exact solution of the Navier-Stokes equation for a flow through a circular pipe with some certain assumptions that I am not going to explicitly mention because we will eventually deal with in the later part of the course, but just to have an idea, just that you have an idea, this is the velocity profile that we are bound to get if we are our geometry is this, and here we are considering the viscous effects. Okay, considering viscous effects. Okay, so that's why we are showing the exact solution, and that in that case also the exact the governing equation simplifies a lot because most of the terms are being cancelled out because of the assumptions that we make, such as the fully developed flow assumption, 1D flow assumption. So these assumptions make the equation quite simple. Actually, we get a very linear second order equation. So by solving that, we obtain that the velocity profile would behave in such manner. Okay. So again, to obtain the mass flow, the volume flow rate in this case, we are using this formula. So this is basically the formula that I previously mentioned, just mentioned a while ago. So it is basically CS, rho is not there, so V dot n cap dA. So here V dot n cap gives us this term, could be simplified as V of R, which is the velocity, and the area. So area is the elemental area in the cross sectional area of the pipe. So it will be 2 pi r dr. So how this is obtained, I guess I should leave it as exercise for you all. Just go to your lectures or even the PowerPoint presentations and just find out how the elemental area is taken. So I don't think this is something that I need to mention it here. So I will not mention. I suggest you go to the lecture so that you get an understanding of how this elemental area is obtained. Okay. So we just carry on this integration to find the volume flow rate. So we can also for the case of flow through pipe, we can also devise this volume flow rate as Q dot is equal to area of the pipe, say A pipe is equal to multiplied by the average velocity. Okay, V average. Okay. So mass flow rate, volume flow rate is also equal to the area of the pipe into the average velocity in the pipe. Okay. So this again, the consider average velocity. I guess we will deal in the later part of the course. But right now, just you take for granted that to evaluate the volume flow rate, we can assume that see, we know that for sure that the velocity profile is parabolic here. Okay. But for now, if we just assume that instead of a velocity profile, if we would have considered a uniform velocity profile, okay, say like this, which has a form of this, and which would have a value, say, whose value we denote as V average. Okay, is that fine? So given that this velocity, the value of this velocity is uniform throughout the pipe, then we can just tell that the mass flow rate would be volume flow rate would be equal to the area of the pipe into this uniform velocity. Is that fine?
Yes, sir.
Okay. So thus the integration that we obtain after doing this, the value of the integration that we obtain after doing this integration should be equal to this value, right? So that's why you can see that after doing the integration, we finally equate these two values, that area into V average is equal to pi r square, is equal to pi r square V max by 2. That is the value that we obtain after the integration. Okay, this one. So this relation basically gives us the relationship between that average velocity and the maximum velocity that is obtained in a pipe flow, in a laminar pipe flow, for the case of the flow through a circular pipe. Okay, this is the value of V max. So we are finding a relationship between the V max and this average velocity. Okay, so for the case of let me write it down, laminar flow through a circular pipe, this is the relationship between the average velocity and the maximum velocity, okay, which is obtained in the center line of the pipe. Okay, similar to that, following a similar derivation or similar understanding, we deal with flow through a pipe, turbulent flow through a circular pipe. Here the flow is taken to be turbulent, and personally I may say, like, I don't know how this, or at least I have not personally solved an analytical solution to find this relationship, the value of the velocity profile. So I must say this this must have been obtained empirically. But even but with that understanding, we find that the velocity profile can be approximated to have such form, okay, such analytical form, in the case of a turbulent flow through a circular pipe, where where velocity profile is given by V max into 1 minus r small r by capital R to the power 1 by 7. Okay, here small r denotes the radial distance from the center line, and capital R denotes the center of the radius of the pipe. Okay, let me just draw it for your understanding. So this is the pipe. So this is the center line. Then this is the, say, at a particular point, this is the radius or the radial distance from the center line, and this complete radius is denoted by capital R. The radius of the pipe is denoted by capital R. So this is what the notations are. Then following the similar calculations, we evaluate the same integration. We know VZR, we know the elemental area. Elemental area will remain the same no matter what the flow is. Even the flow is laminar or turbulent, it doesn't matter. It is a geometrical feature that only changes with the geometry. So this will remain constant. And again, pi r square to V average. Okay, same, implying the concept of average velocity. So after we do that integration, I have done it. So I don't think it's necessary for me to show it step by step. But after we do the integration, it's basically substitution or change of variables. So after we do that, we find that the maximum velocity is equal to 1.224 into V average. So this is the relationship between the maximum velocity and the average velocity. Okay, so again, this is something that I found out from my calculation, but in the lectures it is given as V max is equal to 1.22 of V average. Okay, so this is also quite correct. So just not to be confused that this is 4, it is 2. So this is what I personally find out after performing the integration. So there's no big issue in that. Okay, both are correct. At least the first 3 digits match. So that's completely fine. Okay. So now we deal with one problem that was, I guess, well discussed in the lectures by Professor Gupta. So we'll discuss it again. So let me go to the question. Okay, consider a water storage tank fed by a pipe of diameter 10 centimeter. Let me underline the key points. Of diameter 10 centimeter and drained by a pipe of diameter 6 centimeter. Since it is a circular pipe, the area diameter helps us to achieve the area of the pipes. So diameter at the inlet is 10 centimeter and diameter at the outlet is 6 centimeter. The water enters at a uniform velocity of 3 meter per second and leaves at the, again it's uniform velocity, I have not explicitly written it, leaves at a uniform velocity of 2 meter per second. See, if it is not uniform, you cannot explicitly give a value of the velocity, right? It will actually be a profile which will be a function of the coordinate along which the velocity varies, right? So since we are given a specific value, it basically means that we are ought to treat the velocity to be constant throughout the cross section, right? So that's why we are giving some constant values, 3 meter per second, 2 meter per second. So we are asked to calculate the rate at which water level in the tank rises if the tank diameter is 5 meter. So this is the diagram. So is the question clear? Like, I guess it's quite straightforward, but is the question clear? Yes, no.
Yeah, yes, sir.
It's clear, right? So I have a so okay, by looking into it, by only looking at the flow parameters and the diagram, do you believe, what do you think the outcome would be? Would the would there be a rise in the water tank level of water in the tank, or would there be a decrease in the height of water in the water level in the tank, or the uh, this water level would remain constant in the tank? So what do you feel?
There will be increase in water level.
Why so?
Sir, because the water which is coming, the inlet diameter and its velocity is also greater than the outlet diameter and its velocity.
Yes, yes, very good, excellent. So you can clearly see that if we consider our equation, it's a very good observation. That's what I wanted to point out. Thank you, Sriniket. I guess it was right. It was Sriniket, right?
Yeah, yes.
Okay, thank you. So considering the mass conservation equation, just so it was rho AV in minus rho AV out. Given that we assume that rho is equal to constant, right? And here, as you have rightly pointed out, here since both the area and velocity at the inlet is higher than the velocity at the and the area at the outlet, so it basically means that this term would be greater than this term, right? This term will be greater than this term, so this will give us a positive value, right? So basically it tells us that dm by dt is positive. Again, here dm by dt does not imply that there is a increase in the mass of the system, right? But there is a local increase in mass of the system, of our local increase in our control volume itself. Okay, not that we have created some additional mass here. The flow is constant, so we are not creating any additional mass here. Okay, but in the regime of the control or in the confinements of our control volume, there is a local rate, there is an increase in the local rate of change of mass. That's all this term is trying to imply. Okay, so we see that since this term is positive, we see that the mass of local rate there will increase in the rate of change of mass in the control volume. So if density and area remains constant, so basically means that the volume of the water would increase. So so since volume increases, so it basically implies that since area remains constant, so it basically implies that the height would increase. So following that notion, so we can define our control volume like this. Actually this is control volume, or the idea of the control volume is, okay, I guess the inlet and the outlet is given, control volume we have to choose. So this is how we choose our control volume. See again, here the choice of control volume is also crucial. So could anybody tell me the key feature of the choice of this control volume, like why this kind of control volume are chosen? This dotted blue line, dark blue lines are the control volume. This is the control volume. Yeah, so like why not here? Like why not this? Or why not this? Or why specifically this? Can anybody point out? You can give it a try, there's no issue. It's completely fine. Just give it a try, like why do you feel such control volume was chosen? See, all the control volumes, possible control volumes that I have shown you are well and correct. They can be chosen. There's no harm in choosing those control volumes. But with the choice of those control volumes comes along their own complications. So the choice of this control volume or this control volume is found to be the most ideal for this particular scenario. So could anybody please tell me, like, what is that thing that makes this control volume quite ideal for this case?
Sir, here, while if we consider the outlet control volume also, here the radius, the area will not be equal.
Outlet here.
Yeah, yes, sir. Till here, if we consider the control volume, means the layer, boundary layer, then here they have given it the diameter of the tank as 5 meters, so it won't be considered.
No. Okay. Nice. That's fine. But any that thank you for pointing it out. That's correct. But anybody else, like, it is actually dealing with the velocities. Velocities are the key point here.
Velocities will be like, they will be very less when they are in contact with the surface.
But it is in contact with the surface here. Okay, no issues. Thanks for trying. I appreciate that all of you have tried. So the key feature is that the velocities at this particular point, at the inlet or at the outlet of this incoming pipe here, and the velocity at this point here is defined in the question. Okay, it is being told that the velocity at these points are uniform. That's important. It's uniform. So the velocities at these points are well defined. So because we don't know what the velocity will be at this point or at this point, even though the area is same, the viscous effects might come into picture, and the flow, just saying that it is not considered here, then it eventually means that there is no viscous effect throughout the pipe. But I'm just saying that because of there is some blockage here, or some certain scenario may come out which may modify this velocity profile. Okay, same case goes for this also. It may modify it. But since we are explicitly told that the velocity profile is uniform at this point and at this point, so a simplifying approach, or an approach that simplifies our problem, would be in such manner that we choose our contour volume in a manner that covers or cuts these points. Just a minute. So the contour volume cuts these points where the velocity profile is well defined. So this is very key feature. It's a very key feature while choosing our control volume. At least the velocity and the inlet or the outlet, or at least at one of those points, must be well defined, so that we can do out the future calculations, or if needed, find the velocity at one of the points, let's say at the inlet or outlet. So one must be at least well defined. So this we should keep in mind while deciding our contour volume. So this helps us to simplify our problem a lot. Okay, so I guess I was clear. So keeping that in mind, since we are asked to deal with the change in height, so we will just apply the simple mass conservation. So applying RTT to the mass conservation, obviously. So this is the form of the equation that we obtain. Then since rho is constant, rho could be taken out of the integral. It could be taken out of the time derivative as well, because it's independent both of space and time. d rho by dt is 0. Right? The complete derivative is 0. Right? The density might change with the time as well as space, right? In the case of Eulerian approach. So we are saying that since density is constant, then it will be independent of this spatial integral as well as this time derivative. So it comes out, it can be taken out of the derivative and integral as well. So then this term basically becomes the integral of the of our contour volume. So we can basically say that this is equal to the volume of the tank. Okay, so this is equal to volume of the tank. So volume of the tank we can write as AT into H. Here also there is some certain assumption that I will tell you. So and this term, again I told that since rho is equal to constant and velocity remains uniform at the inlet and the outlet, right, as per our question, so this term can be simplified into this. Okay, right, and since 80 is also constant, the area of tank remains constant. Now you may ask, right, sir, like here in this point the area is varying, right? But just to simplify our case, we can say that we this okay. In fact, we can increase its height even further, so that our approximation is more relevant. So we can say that up to here, say yes. Okay, just consider that. So up to this area, up to this point. Sorry. Up to this point, at least the area of our control volume remains constant, right? Up to this point, it's only this particular region, at this particular region, that our control volume is changing, right? So if we disregard this, the effect of the area at this control, if we, at this point, we can essentially tell that the area volume of the control volume can be written as AT into H. Is that fine?
Yeah, yes, sir.
Is equivalent to, you can say, AT into H. It's a very good approximation. See, the very necessity of applying the Eulerian approach was to get a understanding, or was to get an idea of how the flow features may vary if we consider, given that we are implementing some certain simplifying assumptions. This was the very fundamental reason because of which we developed, or the Eulerian approach was developed, right? So this assumption, you may say that in a molecular level, or in a very small scale, this change in area can have some effect, right? That can have effect. Obviously, it would have effect. But since we are only trying to look at the broader scale, or trying to get an idea how the height would vary, or what is the trend of the variation of the height. So the assumption that this area, this volume is almost equivalent to considering this volume is well and good, at least in the case of Eulerian approach. So these are the assumptions that you can easily make. Okay. So given that your choice of control volume satisfies or helps in simplifying the dealing with the velocities. Okay. So given that this assumption is well and good, you can make this assumption. So this is the assumption that I have made here. So since area is constant, because the diameter of the tank is constant, AT can be taken out of this derivative, right? And here again it will just become a complete derivative. Why? Because height is only a function of time here now, right? So this partial derivative takes converts to a complete derivative here, and these terms exist. So just playing with these terms and modifying the equation, we get that dH by dt is equal to rho A in V in minus A out V out divided by rho AT. And since density is constant, we are dealing with fluid density itself, so rho can be cancelled out. Then we plug in the values that were given to us. Area would be pi by 4 d square, in velocity is given again here. Again the velocity in the outlet is given. Diameter the outlet is given, diameter the inlet is given, and again diameter of tank is given. Just plug in those values in this equation. We find that the rate of change of, or the increase of the height is given by 0.92 millimeter per second. Okay. So was the problem clear, like how we applied the RTT, the concept of RTT, the choice of control volume, cancelling out the terms, like, is that clear? Okay, since no one is responding, I believe it was clear. So since it's a very simple question, well discussed in the video lecture, so you can again revisit the lectures if you want further clarification. So there's no big issue, that's fine. Okay, moving forward, we again now, since till now we are discussing with dealing with the integral form of mass conservation, or the conservation equations. Now we deal with the differential form. So there are different ways in which we can devise this differential form, but Here we will just follow the similar steps that have been discussed in the video lectures. So this is the differential from the mass conservation that we obtain for a Cartesian coordinate system. So how this is achieved? This is achieved by assuming the fact that again we imply the Gauss divergence theorem in the in the mass conservation to the control surface, the surface integral that we are dealing with, and imply some certain assumption, that is stationary control volume and non-deformable control volume. So keeping those assumptions in mind, we can simplify our term and just get and find that the integrand becomes 0. So once the integrand becomes 0, this is the form of the mass conservation that we are left with. Okay, so you may think like, why I am not going with the derivation. I can suggest this can be looked into in the video lectures as well as a standard fluid mechanics book. So I won't go to the derivation, but if you have any doubt in any case, you can ask in discussion forum, and or in the at least after the class is finished, if we have some time, we can discuss it. But right now, to save time, I don't think I will go to the entire derivation. But just to note, just keep in mind, the differential from mass conservation takes this form. Okay, so essentially this is in a vector form. Okay, valid for all coordinate system. Again, this is a very important point. Valid. Okay. Valid for all coordinate systems. Okay, so at least in our fluid mechanics domain, we usually deal with 3 types of coordinate systems. First is Cartesian. Can you name the other 2? That's fine. We deal with a cylindrical coordinate system and the spherical coordinate system. So the choice of coordinate system depends on the geometry that we are dealing with. Okay, if you are dealing with a flow between 2 parallel plates, or a co-ed flow, right? Not as Taylor co-ed flow, but simple co-ed flow with a flow between 2 parallel plates where one of the plates is moving. That co-ed flow we have nicely discussed in the first lecture or the second session itself, so I won't go with it again. So if we are dealing with such kind of flows, then we can devise our governing equation in the Cartesian coordinates, right? Then again, if you are dealing with say a flow through pipe, right, or Taylor co-ed flow, like or rotation of shaft in a confinement, right, or rotation of shaft in a confinement, then again we those cases, or ball bearings, in those cases we will or bearings, not ball bearings, bearings, in those cases we deal with cylindrical coordinate system. And again, for if you are dealing with some spherical shells, like we need to design a spherical shell to handle high pressures. So in those kind of scenarios, we deal with spherical coordinate system. So the choice of coordinate systems comes along with the geometry that we are dealing with. Okay, it depends on the geometry that we are dealing with. Depending on the geometry, the choice of coordinate system will change. But the vector form is universal and is valid for all the coordinate system. Like if there are any other coordinate system that we can create or define, it will be valid for that also. Okay, but for since say if you are trying to write this equation in the in Cartesian coordinate system, so this will be the form of the mass conservation. Okay, differential form mass conservation in Cartesian coordinates. So again, we can again simplify, or derive this equation further, I won't say simplify, or derive this equation further. So since here nabla acts as a differential operator on rho v, so we can say that we can write this as these two terms, that rho del dot v plus v dot del rho. And now if we shift this term here, then we can write dou rho by dou t plus v dot del rho plus rho del dot v equal to 0. And this term, I guess most of you would be quite familiar with it when we are discussing with acceleration. This term or this operator, rho by dou t plus v dot del, this operator is actually the complete derivative, the operator of complete derivative, right? In the Eulerian approach. So keeping that in mind, we can write this term as complete derivative of the density. So d rho by dt plus rho del rho into divergence of the velocity. Okay, and actually this form has a special name. This is the non-conservation form. The mass conservation. Okay, funny naming, but this is the standard name that is being given to such kind of governing equations. Non-conservation form, and this is essentially the conservation form. Okay, so again this is one example that okay, again if we consider incompressible fluid, basically means that complete derivative of density is 0. Okay, see, complete derivative, it means that the change of density with respect to time as well as space is 0. So basically means that density is neither a function of time or space, it is essentially constant, and that's why this term, the complete derivative d rho by dt is equal to 0. So it basically means that if this term is equal to 0, if it goes down, is equal to 0, sorry. So we just left with this term. So rho is considered to be constant. We can just take it as and having some certain positive value, we can take it in the denominator. So it essentially gives us the divergence of the velocity field is equal to 0 for a incompressible fluid. Okay, it does not need to be steady or unsteady, but for incompressible fluid. Okay, it's very important. Here you may feel that we are discussing for steady case only, but no. For steady as well as unsteady cases, but if the flow is incompressible, this is the mass conservation. This is the equation for mass conservation. Okay, and in Cartesian coordinate system, it basically gives us dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. Okay, for Cartesian coordinate system, cylindrical will have its own respective form as well as the spherical will have its own respective form. Okay, so I have not written it, but they will have their own form. But for Cartesian coordinate system, this is the form of mass conservation for a incompressible flow, okay, or incompressible fluid. So okay, keeping that in mind, so we are given some examples. Again, we dealt, this is being discussed in the video lectures. So I will since we have a lot to cover, I guess I will just pass through some problems since these are well discussed, so that we can cover some additional questions. Okay, so it is given that v theta is equal to k by r, where k is some constant and v are equal to 0. See here again, theta and r. So you can clearly see that this is not a Cartesian coordinate system. Now since we are dealing with theta and r, so we are essentially in a domain of cylindrical coordinate system. Okay. So for cylindrical coordinate system, again we are given that the flow is 2d velocity. This flow is 2d, so we have 2d. It basically means that we have two velocity components, and it is an incompressible flow. So if the flow is incompressible, the mass conservation takes the form of the divergence of velocity field is equal to 0. Okay, so we'll essentially write this divergence of velocity field for the two velocity components in the cylindrical coordinate system as this. So the divergence of velocity for cylindrical coordinate system can be written as this. Okay, I'll go go fast because I need to cover a lot more content. So if you need any clarification, please go to the lectures. Okay, so again this term 1 by r dou v theta by dou theta will be equal to 0. Why? Because v theta is only a function of r, right? So any derivative with respect to theta for the v theta component would be equal to 0. So it essentially gives us 1 by r dou r v r by dou r is equal to 0. So it basically gives us this. Again, if it is goes to numerator, it will become 0, right? Obviously for some finite values. Again, then so this term gives us r v r would be a function of a theta, would be a function of theta and t, right? We can also consider z, but why not z? Because this is a 2D velocity field, so only the theta component of velocity exists, and obviously it can be a function of time. Since I told that it's not necessary that the flow is steady to have this equation valid. If the flow is incompressible, this is the mass conservation equation. Okay. So we are left with VR would be equal to f of theta by t by r. So this is our radial velocity component. So there are some special cases. So if f theta by t is equal to 0, then VR would be equal to 0. This is also a valid case. So it will essentially give us a free vortex. So we will deal with this concept of free vortex and this bathtub vortex or sources and sinks when we are dealing with the potential flow. Okay, so this will be dealt in the later part of the course, so let's not emphasize upon it much. Okay, so now we deal with stream function. We discussed briefly on stream function, and this is a very important concept. Why? Because given that the flow is 2D, steady and incompressible, given that these three scenarios are well satisfied, we can implement stream functions to solve that flow field. Okay, because say if the flow field is okay, while we are defining it, we will eventually see how the stream functions helps in simplifying our governing equations. Okay, so if the flow is steady and incompressible, this is the form of governing equation that we will deal with, right? This is the mass conservation equation. We equate the volume flow rate at the inlet and the outlet. So this is it. Again, just some observations. The spacing between the streamlines increases where the flow slows down and decreases where the flow speeds up. Okay, so essentially means that the flow at this region is having lower velocity compared to flow at this region. So I won't go to detail or to the explanation. You can follow the lectures for that. Again, this is one important point. This I will read it out. Just you can remember is a point. So stream function psi and xy, where psi we denote the stream function as psi, which can be a function of x, which is a function of x and y. So stream function psi x of y is a function which takes the constant values for a given streamline. Okay, the stream function has a constant value for a given streamline, such that the difference of values of this function for two streamlines gives the flow rate per unit depth between them. Okay, so this is just a definition or a definition that it's well and good if you remember, and detailed derivation I guess we don't have time to cover that, but if you want you can just go to the books or the lectures once again. Yes, so this is for for Cartesian coordinate system. I again emphasize the coordinate system because sometimes people may get confused by seeing different forms of the definitions, but the definitions of the stream functions vary according with the Cartesian coordinate that is being used. So for a Cartesian coordinate system, this is the definition of the stream functions, that u is equal to dou psi by dou y, and v, the velocity component along the y direction, would be minus of dou psi by dou x. Okay, and you will eventually see that this definition of stream functions inherently satisfies the continuity equation. Again, now since psi is constant along a streamline, the derivative of psi would be equal to the derivative of psi could be written as dou psi by dou x dx plus dou psi by dou y dy, This is the definition of a complete derivative. So if I must say complete derivative of psi, if psi is a function of x and y, okay, and since psi is constant along a streamline, d psi will be equal to 0, right? It will be equal to 0. Then we can essentially write dou y by dou x equal to minus dou psi by dou x by dou psi by dou y, right? This is equation 1. Consider it to be as equation 1. Again, from the equation of streamline, we know that dou y dou x is equal to v by u, because the streamline essentially gives us behaves as a tangent to the velocity vector at that particular point, right? So this is the definition. So combining these two definitions, we obtain the relation u is equal to dou psi by dou y and v is equal to dou psi by dou x. Okay. Again, for C, as the coordinate system is changing, the definition also changing. Definition has also changed. For in the case of two-dimensional cylindrical polar coordinates, the velocity components in the r and theta direction are given by ur is equal to 1 by r dou psi by dou theta and u theta is equal to minus dou psi by dou r. See, this is a very clever technique to remember these things. See, you may see, like, if you compare the dimensions, you will see that u is equal to, say, if this is our quantity, u is, say, is varies as velocity, would vary as psi. Say psi, we denote the dimension of psi as capital psi, say, and divided by dimension of some length. Okay, so the velocity has a relationship with the dimension of psi as 1 by l in the dimension of psi. Okay, you can see the similar trend is followed here. The u is equal to psi by y has a dimension of l, again x has a dimension of l. Okay, similar to that, in at least for u theta, you can see that it is dou psi by dou r, so r has a dimension of l. But here, since theta is dimensionless, we need to satisfy this condition, right? We need to satisfy this condition. So that's why there would be a multiplication of 1 by r, so that this condition is satisfied. And thus ur is equal to 1 by r dou psi by dou theta. Okay, this is just a technique to just cross verify whether your definition that you have written is right or not, because sometimes you may forget and may shift 1 by r here also, but just to check, you can check it like that. Okay. So this is one another example dealing with stream function. So it is given that stream function is equal to psi. Stream function is given by psi equal to 3x square minus y cube. Okay, and we are asked that whether the flow is incompressible or not. So to do that, we can find out the velocity components. So you know u is equal to dou psi by dou y. So we take the derivative of psi with respect to y. So we get minus 3y square. Then again the v is equal to minus dou psi by dou x. So we take derivative of psi with respect to x and with a minus sign ahead. So it will give us minus 6x. So since we know now we know the u and v velocity components, we basically take this calculate the value of this one, this derivative dou u by dou x by dou v by dou y. So once we do that, we find that dou u by dou x equal to 0. Why? Because u is only function of y here. Again, v is only function of x, so dou v by dou y is equal to 0. So essentially, it essentially gives us that dou v by dou x plus dou v by dou y is equal to 0, and that's why the current flow, the given flow, is incompressible. Okay. So there's one more thing I just want to tell you. See, I have written here that the stream function inherently satisfies the 2D continuity equation. Okay. See how we can prove that. We know that u is equal to dou psi by dou y, right? Let me clear. Dou psi by dou y. Again, v is equal to minus dou psi by dou x. So the continuity equation gives us dou u by dou x plus dou v by dou y equal to 0, right? Oh, sorry. Just to say that we know that, then we evaluate this. So dou by dou x, we substitute u here, dou psi by dou y plus dou by dou y into dou psi by dou x. So you can clearly see that it gives us dou square psi by dou x dou y minus dou square psi by dou y dou x. And if we assume that the psi is a smooth function, the order of derivative would become irrelevant. So it will essentially give us this equal to 0. So you can clearly see how the definition of stream function inherently satisfies the continuity equation. So this is again a very key feature. Once you are well versed with this concept, you will see how extremely correlated the definition of stream function and the very definite how the continuity equation can be related, or how the stream functions are related. Stream equation of streamline is related to the equation of stream function. Those you will see. So you only be clear when you get the hand of it, like when you go through it again and again. So that's it. So again, I will leave this example right now. So okay, now we deal with Bernoulli's equation. Okay, so one of you asked me regarding the energy, like how the energy is dealt with. So here we will deal with the energy. We will get an idea how the energy is being conserved in the case of fluid flow. So since I must say, since we are quite what to say, we have quite limited time. I don't think I will go through details of derivation. I will just say that the derivation of the Bernoulli equation starts with the first law of thermodynamics, that is change in the energy in the energy of the system is equal to the net rate of change, net rate of heat input minus the net rate of work output from the system. Okay. Again, E can be dissociated into the mechanical energy and the internal energy, where mechanical energy consists of the kinetic and the potential energy. So all of you, Francis, Prabhajan and Sinigat, I kindly forgive me that I have to go a bit fast so that I can cover up the concepts and also deal with some problems that will be more beneficial for you all. So I'll go through it quite fast, okay? And if you have any doubt, please go back to the lectures. So again, so the energy per unit mass can be devised or written in this form. So if we implement RTT to the energy conservation, so this is the form that we get. So for steady flows, again this term would be equal to 0. Why? Because the local rate of change of energy with respect to time is 0. So this would be equal to 0, and we have d by dt is equal to this one, and this would be equal to this from the first law of thermodynamics. So we equate these two terms, and for most of the general fluid flow cases that we will not deal with heat interaction. Okay, interaction of effect of heat interaction in fluid flow, I must say it has a separate subject to deal with it, that is known as heat transfer. We extensively discuss the effect of heat transfer or heat interaction in fluid flow, or essentially or specifically how fluid flow has certain implications of heat transfer rate. We extensively discuss it on in a course called heat transfer. So for a general day-to-day life problems, we will not deal with the effect of heat transfer in fluid flow. So we can just disregard this term for right now. So if you disregard this heat interaction term, you are only left with this equation: rho AV out minus rho AV in is equal to minus of the net work output from the system. Okay, net work output, because the work done as per the usual convention that we use in thermodynamics, the net work output from the system is considered to be positive, and net work done on the system is considered to be negative, right? So keeping that assumption in mind. Okay, so this for deriving the Bernoulli equation, these assumptions are highly important. Okay, why they're important? I guess it is well discussed in the lectures, but still I will go through the read through the assumptions at least once here. See, for the Bernoulli equation to be valid, the 2 points at which we are applying the Bernoulli equation should lie on the same streamline. Okay, this is the first assumption. Second is the flow should be steady. It is how we have disregarded this term, right? That's right, the flow should be steady. The flow should be incompressible. Basically, the density remains constant. And finally, the flow is inviscid. Again, a very key assumption that we make for the validity of the Bernoulli equation. So each and every time, whenever you are going to apply Bernoulli equation to solve a fluid flow problem, you must keep in mind that these conditions are satisfied well ahead. Okay, these conditions must be satisfied for you to be able to apply the Bernoulli's equation. Okay, so keep these assumptions in mind, okay, all the time. Again, there is no net thermal interaction, so basically Q dot is equal to 0. So keeping that in mind, again, this equation, the hash denoted by hash, that is rho AV E, where E is the net energy interaction per unit mass, 2 minus rho AV E minus 1, or it is basically the energy flux to the control volume, is equal to the negative of the net work output. So what are the possible ways through which work interaction can take place? That is, one is through work done by the normal pressure forces at the inlet and outlet. Okay, this is essentially the flow energy, or the energy that is required for the flow to exist at the inlet and outlet. Okay, to push the flow through the inlet and outlet. This is the work that is being done by the normal pressure forces. Okay, at the inlet and outlet. And also, we may have work done by the shear stresses, but we see that the work done by shear stresses can be neglected. Why? Can anybody please tell? The work done by the shear stresses is equal to 0 in this case. Why? Can anybody please tell? It's a very important output or important result. Why is the yes?
Because shear stress acts perpendicular to the object. It is perpendicular to the beam.
Actually, shear stress always acts along the surface of the object, along the surface of the along which the force is acting. So it will act along the surface and not perpendicularly. So this is first point, but there is no issue. That's completely fine. But I am asking, why is it 0? See, okay, that's fine. This would be equal. I guess your general answer was by looking at this dot product. It's not the case. But if that happens, that the shear direction of shear force and the velocity is perpendicular, then the shear force will be inherently mathematically will be equal to 0. That's fine. But here, the shear forces are essentially 0 because we are disregarding the viscosity, right? Viscosity or mu is equal to 0. Or essentially, I must say mu cannot be equal to 0 because then it will not be a real fluid. So I must say the shear stress tau is equal to mu del u by del y. This is equal to 0. Basically, the velocity gradients don't exist. Since the fluid is inviscid, the velocity gradients would not exist or would be so low that it won't be able to manifest the shear stresses or the shear stresses that in turn come out as the shear forces, right? Multiplied by the lateral surface area or the surface along which the shear stress acts, right? Since the velocity gradients don't exist, there is no point of having shear forces, and since there are no shear forces, the work done by the shear forces would be equal to 0. Is this point clear? Yes, no would be fine. Okay, so I hope it was clear. Then again, the work done by pressure forces can be denoted by this derivation. I suggest that we go through the lectures. So I'll just again skip through some points. So substituting those values in the energy conservation, we get that V2 square by 2 plus dz plus u plus p by rho at 1 is equal to v square by 2 plus dz plus u plus p by rho at 2. So this term is essentially constant at 2 points. Okay, the sum of these all terms at the 2 points are constant. Okay, but again, since we are not dealing with thermal action, the temperature of the fluid will remain constant, right? Because the internal energy is a function of temperature only, right? So since that's the case, so we would have, you can disregard this term, so we would finally have p by rho plus v square by 2 gz plus p by rho plus v square by 2 plus dz. Again, I have done a mistake here, so this at point 2 is equal to 0, that also along a streamline, right? This is the first assumption that we took. Points 1 and 2 must be along a streamline. Okay, and these terms have their own importance. Okay, have their own importance and are known by their special names. So this term is known as a flow energy head or pressure head, as mentioned in the lectures. This term is the kinetic energy head per unit mass, and this is the potential energy head per unit mass. Okay, so, and again there is one more important point that I want to emphasize. Just remember it, because I guess we will use this fact in our one of our problems that we are going to discuss today. Okay, points 1 and 2, see, points 1 and 2 can be any 2 points in the flow field if the flow is irrotational as well. Okay, is that clear? See, we are telling that for the validity of the Bernoulli equation, the 2 points that at which we apply the Bernoulli equation should lie along a streamline, should lie on the same streamline. But now I am saying that if the flow is irrotational, this is basically the cross product, the curl of the velocity field is 0. If this is the case, then point 1 and 2 can lie at any points, like at any points in the flow domain, at any 2 points in the flow domain. Is this point clear? Please say yes and no, because this is very important concept.
No, sir. Nothing else.
What? This is not clear?
No, sir.
Okay, see, for exact clarity or the mathematical understanding of this fact, I guess you need to go through the derivation of the entire derivation of the the Bernoulli equation from the Euler's equation. Okay, but I guess this is out of the scope for the current course, but I'm just saying, please remember this point, please take this point for granted, that see, we initially assumed that points 1 and 2 should lie along a streamline for the validity of the Bernoulli equation. Is that point clear, Sriniket?
Yeah, yes, sir. This point is clear.
Okay. Now I am saying that if the flow is irrotational, that is the curl of the velocity field. You know the definition of curl, cross product. Do you know that? Sriniket, Prabhajan, Francis? For a 3D Cartesian coordinate system, if u, v and w are the velocity component, then curl is basically given by the determinant, by the following determinant. So this is the curl of velocity. And if this is equal to 0, it implies that the flow is irrotational. I hope you now get it. So if this is the case, if the velocity field satisfies this condition, basically the flow field is irrotational, then the points 1 and 2 that we eventually told that should lie along a streamline may not be on the same streamline. The point 1 and 2 can lie at any 2 points in the flow domain. Is that clear now, Sriniket?
Yes, sir.
Okay. So this is very important. Okay, what I am telling to all of you, Prabhajan, Francis, and Sriniket, like this is a very key understanding. Like this is the case, then point 1 and 2 can lie at any 2 points in the flow domain, given that again the flow is steady, incompressible, and inviscid. Okay. So, okay, so let's discuss this example. Take this example. I'll zoom out a bit. So this is Torricelli's equation. Okay, this was I guess well discussed in the video lectures by Professor Gupta. So here we assume that there is a tank, water tank, and there is a opening or orifice or outlet, I must say, at its bottom end. Okay, so this is the outlet, and we assume that the fluid will go out from this outlet. Okay, we follow this trajectory. So flow will go out from this. So we assume again, to apply Bernoulli's equation we need to take some certain assumptions. First we assume that the points 1 and 2 here, points 1 that is at the free surface and point 2 that is just at the outlet. Points 1 and 2 should lie on the same streamline. First assumption. The flow should be steady, the flow should be incompressible, and the flow should be inviscid. And again this point, no energy interaction. Okay, this one is also there. And no thermal interaction. So given that all these points are satisfied, we can now apply Bernoulli's equation at these 2 points. So the Bernoulli's equation at these 2 points would have this form. It's V1 V square by 2 plus dz plus p by rho plus V square by 2 plus dz plus p by rho at point 2. So V1 would be essentially be equal to 0, because the rate at which the flow is, we assume that the rate at which this height or this height is decreasing because of the release of fluid from this outlet is very low. So if we assume that, then V1 can be treated to be equivalent to 0. Gz1 will exist. Again, we assume that both pressure at the point 1 and point 2 is equal to atmospheric pressure. Pressure is not 0, okay. Gauge pressure may be 0, but the absolute pressure is not 0. So we tell that the pressure at point P, this point 1 and point 2 is the atmospheric pressure. So we tell that since both are atmospheric pressure, we can cancel out both the terms from these equations. So we're essentially left with V2, these terms, V2 square by 2, Gz2 and Gz1. So we essentially write it as V2 square is equal to 2G Z1 minus Z2. And since Z1 minus Z2 is equal to capital H, here we can write that V2 is equivalent to, so it will be better if I write equivalent, equivalent to root 2GH. And following the same criteria, then the volume flow rate would be equal to A2 into root 2GH. Why A2? Because this is the area at the exit. Okay, A2. So this is one example. Okay. Then we deal with siphon. Okay, the working of siphon and its applications, I guess it is well discussed in the lectures. But still, I will just show you how to apply the Bernoulli's equation in the case of a siphon. Okay. So similar to the previous case, we consider a tank. Okay, we consider a tank here, water tank here, which or a fluid which contains some fluid, and then we assume that there is a pipe which is devised in a manner that its exit lies below the surface level, below the free surface level of the container. Okay, this is the free surface level, right? So the exit is below the free surface level at a height h. Okay, it is lower than the free surface level at a height h. Okay, so first of all we apply the Bernoulli's equation at point 1 and 2. Okay, say this is a streamline here, this is a streamline here that we have considered. So this is a point 2 and this is point 1. Point 1 essentially is just at the inlet, like just at the inlet. Okay, here. So again we can apply the Bernoulli's equation at these 2 points, P1 by rho plus V1 square by 2 plus dz1 equal to P2 by rho plus V2 square by 2 plus dz2. Okay, again P1 and P1 is considered to be P ATM. So if you are just dealing with gauge pressure, so this can be striked out. Okay, gauge pressure, not the absolute pressure. So if you are telling as gauge pressure, then this can be striked out. That's fine. Then V1 is again essentially 0, because we again assume that the rate of decrease of height at this is considerably lower than the because of the rate at which the fluid is exiting from this exit. Okay, so V2 would be there, V1 is equal to 0, V2 would be there, P2 we need to find out, and Gz1 and Gz2 we know, because we know the difference in these 2 levels. Okay, these 2 points, this is essentially H. Okay, and V2 is, now we say that at the exit we imply that the velocity at the exit, we imply that let us consider it as root 2gs. Okay, I am just giving it a particular value. Okay, and you will see that this is a very good approximation, but just for names, for the current scenario, assume that this is the velocity at the exit. Okay, here at the exit, not here. Okay, we don't know what is the velocity here, but at the exit we are saying that it is equal to 2gs. That is, we essentially know the velocity at the exit. But now, since the area at the exit and at the point 2 are equal, and since density is constant, right, and we are disregarding the viscous effects, we can essentially tell that A2 is equal to A exit, so it essentially gives us V2 is equal to V exit. From where? From the mass conservation, right? So keeping that in mind, we can substitute V2 as V exit. So P2 can be essentially being derived as P2 would be P2 by rho will be equal to minus GH. Why minus GH? Because Z1 minus Z2, right? So since point 2 is at higher elevation than at point 1, so Z1 minus Z2 will give us a negative value, so it is minus GH, then minus V square exit by 2. Okay, here you can see that this term, since G is positive, H is positive, and V is positive, and obviously it is squared, so it will remain positive. So since all these terms are positive, we get a negative term at the right hand side, and it is exactly what we are expected to get, right? You can see that the pressure is negative here, but since in an absolute scale negative pressure has no meaning, the negative pressure that we get here is essentially the gauge pressure that we get with respect to the atmospheric pressure, right? So this is the gauge pressure that we obtain, and this negative gauge pressure is what that acts as a suction, or behaves as a suction or driving force that pulls out or sucks the fluid out of this container to the exit, to its exit. Okay, so this is how Bernoulli's equation is being applied to the siphon. So okay, since we are limited in time, let's deal with this equation. Okay, I want all of you to solve this, both of you to solve this equation. Okay, solve this question. I believe that both of you have a pen and pencil and paper in front of you, right? Yes, no?
Yes, sir, we have.
Okay, thank you. So let's see this question. Okay, so we can zoom out a bit. Okay, so we have a steady 2D flow represented by the following stream function. That psi is ax square y. Okay, this is our stream function, where a is a known dimensional constant. Okay, this is constant, consider it as constant. Now we are told that consider 2 points 1 and 9 and 3 and 1 in the flow field. Okay, consider 2 points P and Q whose coordinates are given. This is in this Cartesian coordinate system in 2D, so it will have two arguments, so it is 1 and 9, 3 and 1. Which among the following statements is or are correct? Okay, so the first statement is the flow field is rotational. This is first statement. Second is the flow field is irrotational. Then Bernoulli equation can be used to evaluate the pressure difference at the points P and Q. Then Bernoulli equation cannot be used to evaluate the pressure difference between points P and Q. So I guess it's quite obvious and quite clear what you have to find out first. So I'll just give you an idea. First you need to find the velocity components U and V. From that you need to check whether this condition is satisfied or not, whether this is equal to 0 or not. Okay, can you both of you please do that fast? We have only a few minutes left. We'll just deal with this question, and if both of you attend the next session, we will deal with some more questions regarding this concept in the next session as well. So could both of you please find out the velocity components and then just tell me what the answer is. It's quite simple, right? Partial derivatives. U is equal to dou psi by dou y, V is equal to minus dou psi by dou x. Simple partial derivatives. So once you find that, you evaluate the curl of the velocity field. So I will write it. I know that you know it, but still. So you can just write it as W will be 0, so I will write it. So Uh, did you find it, any one of you? Velocity components, then the curl of velocity field, whether it is rotational or not, these things. Francis Suniket, did you make any?
Doing,
Yes.
doing, sir, doing the matrix.
Oh, sure, no issues. It is actually determinant. So it's quite a determinant. Francis, any progress? Uh, okay, so no issues. Okay.
Sir, is the flow is
Yes.
sir, here we are not getting zero, sir.
Okay. What you are getting?
So I think it is irrotational, sir. Flow field.
If it is not zero.
Yeah.
If it is not zero, then it means it is rotational, right? If del cross V is not equal to 0, it implies the flow is rotational. Okay, no doubt, I guess your answer is correct. You will eventually see. So, you eventually see that the flow is rotational. Okay, we find out the velocity components, put the values in the velocity field in the determinant, then we find that the velocity field, the curl of velocity field is non-zero, so we can essentially tell that the flow field is rotational. Okay, so
That's it, no, sir. It is not zero.
yes, it means it is rotational. But again, we have some other argument as well, right? It is asked that whether the Bernoulli's equation can be used to evaluate the pressure difference between points P and Q or not.
Sir, maybe if we can do finding the distance between 2 points.
No. See, okay, I'll just tell you how to do that. So, actually, since we know the stream function, right? We know the equation of stream function, and we know that the stream function is constant along a streamline that we discussed. Okay, so stream function is constant along a streamline. Psi is equal to constant along a streamline. Okay, right. So so if these 2 points are on the same streamline, right, if these 2 points are on the same streamline, then the value of this psi, if we substitute the value of the coordinates in this in the definition of psi, then the psi must give the same value, right? Is that point clear?
Sir, like we need to substitute the both points in the psi equation, sir.
Yes. First substitute the value of x and y coordinates in here. So you will get, say, x is equal to 1, then 1 square is 1, then y is 9, right? So 1 into 9 is 9. So you will get 9a, right? This is the first value of your psi. Then again substitute this point, value of this point. Then 3 in x, so it is 3 square, right? So 3 square will give you 9, and y is 1, so it will give 1. So it will again give you 9a. So it essentially tells us that these 2 points lie on the same curve or the same streamline, right? The same stream function. Okay, since psi is constant along a streamline, so we can tell that these 2 points lie along a same streamline. But we again saw since these 2 points lie along the same streamline, then we can say that we can apply Bernoulli's equation. We can apply Bernoulli's equation to evaluate the pressure difference between points P and Q. Okay, since the condition of that the 2 points should lie along the same streamline is satisfied, then it is irrelevant whether the flow is rotational or irrotational. Okay, but again it's important. But if it was a scenario that even if the flow is if the points do not lie on the same streamline, but if the flow was irrotational, okay, if the flow was irrotational, then also you could have been able to apply Bernoulli's equation to the 2 points. Is that clear?
Yes, sir. Sir, actually, like, is it a condition that only if the flow is irrotational only we need to apply the Bernoulli's equation?
No. That only I told, right? If the flow is rotational, then also we can apply Bernoulli's equation, but then the Bernoulli's equation will be constrained to 2 points along the same streamline. Is that clear?
Yeah, understood, sir. If it is irrotational, any point on any different streamlines we can choose.
Any 2 points in the flow field you can choose. It need not be along the same streamline. Okay, so I had actually some more questions in my notes, but I don't think we'll be able to deal it today because of our time constraints. So I guess thank you for attending the session, both Francis, Srinikan and all the other students who were there. So I suggest that since we are not able to cover a lot of questions in this today's session, so I suggest that you join the Monday session as well. I hope the other TA would cover some more questions so that concepts are clear. But I hope that even if we are not able to deal with some lot of questions, we will at least be able to clear some of your fundamental doubts or concepts that is the fundamental necessity of this problem solving session, right? So I hope I was able to clear your doubts, and I hope also that both of you also got to learn something beneficial to both of you. So I hope that our objective was fulfilled by today's session. But again, sorry that because of our time constraint we couldn't deal with more questions. But for that, I suggest that you join the next session. The Monday session, and as well, if you want to discuss the same problems, you can join the next Friday session as well. Okay, we will discuss some problems before starting the next week's concepts. Is that fine, Sriniket and Francis?
Yeah, it's next week.
So actually, it will be great if we can go on straight on more problems instead of theory. Like it's just a suggestion.
Yes, that's the thing. But I am not extensively discussing a theory by myself, right? I guess this is a suggestion given by Professor Gupta as well. But the thing is, some of you asked doubts that I need to clarify, right? And that is one of the key feature of these sessions. Like, you need to clarify the doubts of the students. Like, I just cannot leave them. So I am trying to handle the things, but sometimes it happens that I am asking some questions that whether you are clear with the concept or not. Then some of the students are saying they are not clear. So in that case, I need to clear the concepts, right? So thank you for the session. I hope I will try to deal with more problems in the next session. But I guess again clearing the concepts is also an important what is condition that I need to satisfy. So I hope I hope you understand, Francis. And
Yes, sir.
okay,
Thank you, sir.
okay. Thank you. Then okay, one more suggestion to both of you would be that both of you and all other students who will eventually join the session or are attending these courses, I would suggest that they go through the lectures thoroughly. Okay, they go through the lectures thoroughly. Even follow the books that is suggested by Professor Gupta, so that the concepts are clear. Then in the class, I can only just discuss the very lightly skim past the concept and then discuss more questions. That would be beneficial. So that's one suggestion from my side. I hope both of you take that positively. So thank you.
Yes, sir.
Okay. So thank you then for joining. Then we will meet both of you in the next session. Okay. Thank you.
Thank you, sir.
Thank you.